As we saw earlier in this chapter, one of the rules that aromatic compounds must obey is the Huckel rule, which says a compound must have 4n plus 2 pi number of electrons in order to be aromatic. So where does this rule come from? One way of explaining it is based on molecular orbital theory, and we're going to use the example of benzene and look at its molecular orbital diagram in order to understand the Huckel rule. If we focus solely on how the pi bonds are formed in benzene, we'll have this simplified molecular orbital diagram for benzene. Now, if we include all of the sigma bonds, the molecular orbital diagram becomes way more complicated than we can cover at this level. So we're only going to look at how the pi bonds are formed, which are formed by taking 6 p orbitals, one from each carbon atom. And if we fuse them together, we'll come up with 6 new molecular orbitals, which belong not to the original carbon atoms, but now to the entire molecule. 3 of those molecular orbitals will be lower in energy than the original 6p orbitals. And so you can see that they are below in terms of energy. In other words, they're more stable than the original p orbitals. 3 of the orbitals will also be higher in energy, and so these are considered anti-bonding orbitals. The energy of each of these orbitals increases as we go up, and the lowest energy orbital would look something like this, where the 6p orbitals are completely aligned, where the same faces are facing in the same direction. So that's illustrated here in a simple way by using 6 red colored lobes facing on the top of the molecule, and then 6 blue ones on the bottom. If we introduce a node, in other words, where the faces of these lobes change, so in this orbital, the one on the left, I guess, it changes in going from this orbital to this one here. So there's a phase change there, and there is a node or a place where electrons don't go, basically. And on the other side of the ring, there's again a node. So this molecule actually has a node that traverses the entire molecule. And so because of that node, this molecule or this orbital is higher in energy than the one we have here. There's another example of a molecular orbital that also has a node, now this time going this way, and it cuts across the 2p orbitals on this atom on the left and this atom on the right. That's why those lobes are not shown, because there's a node there. And then there are 2 other orbitals on this side of the molecule which are aligned, and then 2 other ones on this side which are aligned. As we go up, we're going to encounter more and more nodes. So there's actually 2 nodes on this molecular orbital, one going this way, one going this way. And on this one, there's a node here, and there's a node here. And then on the last one, there's actually 3 nodes. And so this is the highest energy molecular orbital. Benzene has not only 6 atomic orbitals to begin with that eventually turn into 6 molecular orbitals, but it also has 6 pi electrons. So once you build the molecular orbital, if we start to add the electrons that we have to work with, which are 6 electrons, 1 at each p orbital, that now when it comes to the molecular orbital will be placed as follows. So 2 will go in the lowest molecular orbital, which is here. So 2 electrons go there. The next 2 will go like this. 1 will go on the orbit on the left, the other one on the right, since these 2 orbitals are equal in energy. In other words, they're degenerate orbitals. Since we have 2 more electrons, we're going to completely fill this orbital, and then we're also going to completely fill this orbital. And that gives us 6 pi electrons, which completely filled the 3 bonding molecular orbitals. Notice we don't have any more electrons to put into the anti-bonding orbitals. As a result of going from 6p orbitals into 6 molecular orbitals and only filling the 3 lowest molecular orbitals in energy, which happen to be lower in energy than the original p orbitals, we're essentially, in making benzene, making the molecule more stable. All right, so this partially explains why having a benzene molecule is more stable than just having these individual atoms, carbon atoms separate. We essentially create a molecule that has molecular orbitals that are more stable than the original p orbitals. This is something that's going to happen with every aromatic compound. If we draw the molecular orbital diagram, we're always going to place the pi electrons into only bonding orbitals, and we're always going to fill them completely. And we're never going to put any electrons into the anti-orbitals. That's not what we see, however, with anti-aromatic compounds. Let's review some of the key points that we learned from looking at the molecular orbital diagram of benzene. One of the things that we saw was that bonding molecular orbitals are more stable than atomic orbitals. And of course, they're also more stable than anti-bonding molecular orbitals. Anti-bonding molecular orbitals, on the other hand, tend to be less stable than atomic orbitals. When I mention atomic orbitals, I'm referring to the p orbitals from which both the bonding molecular orbitals and the anti-molecular orbitals are formed from. As we start to fill in the molecular orbitals, we generally start with the most stable molecular orbitals, which are those at the bottom of the molecular orbital diagram. We start to fill them one electron at a time. And so each molecular orbital will get 2 electrons. Once we use up both electrons, we will move on to the next most stable molecular orbital diagram. If we run into a molecular orbital diagram that is degenerate, in other words, it has the same energy, then we have to fill each degenerate orbital 1 electron at a time. And then once each degenerate orbital is filled with a single electron, we go back to adding a second electron into each of these degenerate orbitals. This is based on Hund's rule. Note that we use this rule in filling atomic orbitals as well. So if you notice, the molecular orbital diagram of benzene has 6p orbitals. Each one has an electron, rather than having 3 that are completely filled and having 3 that are completely empty. As we saw, benzene has 3 bonding molecular orbitals that are completely filled. And so since these molecular orbitals are lower in energy than the original atomic orbital, benzene is more stable due to these filled molecular orbitals that are bonding. In other aromatic compounds, we're going to find the same situation where all of the bonding molecular orbitals will be filled.